So let's start our day one with Verilog. So what is Verilog? This is the first question everyone should know about that. That Verilog is a hardware description language, or it is a language which describes the hardware used to design, model and stimulate design electronics systems. So we will design a hardware like flops, latches, combination circuits, sequential circuit for shorts. So this language will design this thing. Okay, so like microprocessor, memory and digital circuit. So these are the larger part of the circuit, but inside that there is flops, latches or sequential circuit or combination circuit. So it was originally developed in 1984. So this is all the past of this, so we will not go there. So what is the main thing is that it is unlike C or C++ or Python, which describes software behavior. Verilog describes hardware behavior and structure. So software is like it has some sequential kind of steps, like C or C++ compiler has some sequential kind of steps. But hardware, it's not like that. Hardware, if you are using in hardware, you can simultaneously on camera, you can simultaneously on WhatsApp, multiple things are going on a hardware. So it has to store internal process is also going there. So hardware cannot be sequential. It is parallel. It is having a specific circuit inside it. So we need a specific language for describing such complex things. So what physically happens in gate and flip-flops and logic. So what is happening inside your chip or your mobile, inside their hardware, like how electrons are flowing, how the function are going on. We will describe this with the help of Verilog. So first of all, this language is used now from past, from you can see 1984 to till now. It is, we are using Verilog as our hardware description language. So it is very important language. So let's move forward.
Hit subscribe, like, and comment now. Let's begin the journey of verification.
So why we need Verilog? As I said earlier, before HDLs, engineer have to draw schematic of the circuits. Means they have to draw a single flop, then another flop, and it is a slow error prone process. As you can see, our designs are becoming in billions of transistor, not like 10,000 transistor. So it is very complex process, and nowadays it is impossible to draw a schematic or something kind of thing without a Verilog. With Verilog we can write hardware designs as text code, simulate it to the check correctness, synthesize it into actual gates. So in FPGA example are different. FPGA has switches inside that which will connect multiple gates, and we will write that language, and that switches will connect the gates, and you will get a proper circuit out of it. It is a little bit of FPGA introduction, you can say. So we will write a code, and as per that the switches will connect a circuit. For example, NMOS and PMOS connect, it will create a CMOS, and we can use that as an inverter. So that switches will connect like that. So FPGA or ASIC. ASIC is like you are designing a proper circuit, and that will synthesize to a proper circuit. Then you will have send this check, after checking and everything, you will send this to foundry, and you will get a proper ASIC circuit. So you can design with Verilog this kind of things. Gap between design and hardware implementations. So yeah, we can use Verilog easily now. With the help of Verilog, we can now implement a complex hardware. So let's start with our Verilog. You can understand AND gate like this. For example, we don't know what is our AND gate. So we know that AND gate has two input and one output. Okay. So this upper layer, this layer is our module and N module. We will cover this with this box is our module and module. You can understand it like that, and we will describe this input and output. So A and B are input. We will describe its pin of that module A and B, and output as a Y. And in that we will write this logic. We will understand this after your day 2 course, how to write these things and how to write everything. So for now you can say it is a logic. So for syntax we will say it is a logic. So here we will have our logic. So after synthesis, this will look like this gate. So it will have proper A and B function, and we will have y as output. So for syntax, you can understand here is let me change the color. Okay, so syntax, you can see this is our main cover module and module, and it is having a static nature, means our hardware will be throughout the simulation, because it should be throughout the simulation. You have to write a name of a gate, so this box you will call and gate. This is name of this block, and after that you will have a ports. You can write whatever sequence you need to write, like first write input or output, anything, and describe its input, output, and in output is also there if you need. And here it is called a continuous assignment. It is also a block, you can say, and y is output and a and b as a output. So for now we haven't used data types, we will come it in this after the slides. Okay, so for now you have understand that a module is, you can say, a layer of a box. In that we will describe input and output. This is our basic syntax. Now data types. So in Verilog we are not limited to 0 and 1, because it is software related language, and software only considers 0 and 1 because it doesn't have to have a physical or environmental thing interfering with your process. So the software will only have 0 and 1, but in and 0 and 1 is the two state data types. So the variable which have two values like 0 and 1 only, they will have a two state data types. But in hardware we have four state data type, which will have 0, 1 as well as x and z. So this x and z, x is also known as unknown, and this is z, which will be known as high impedance in our language. So as you know, impedance is very high resistance, and unknown is you don't know whether it is 0 and 1. So here we are not using this x as don't care. This is our digital thing in K-map. Don't care is like we don't care 0 and 1 are there. Unknown is like we don't know what is 0 or 1 are there. So these two things are different. So for Verilog language we will stick to our unknown thing. So what is that? Four state data we will know. Okay, so why do we need four state data type? So this is our question, why we introduce four state data type. So because in real hardware not everything is always 0, 1. As I said earlier, if you are creating a real hardware, you have to be ready for a sequence where you don't know the value of 0 or 1, or there is some short circuit in your circuit. For example, this is your circuit A and B. So either A 0 or it will be unknown, but this will have our problem, like where we will know that this is a short circuit, open circuit. How we will know this is a open circuit? So we need some variable to show this. We will use that z. It is high impedance, that it is not connected. Or what happen if there is two wire and here it is 0 and here it is 1? So what will be the value of here? Let's say it is A, it is B, and here it is Y. So what is the value of Y? So here we will use X as unknown. So unknown is like it may be 0 or it may be 1. So similar thing is here. Example, a wire might not be driven yet X, or a tri-state bus, like I have given this open circuit example because it is easy to remember. Two drivers might be driven opposite to values. Okay, now for example, this is wire and here is A, here is B, and you are taking Y here. Here is 0, here is 1. So what is the value of Y? Either 0 or 1. So we will just say it is X, because we cannot have risk with our own hardware, right? So we need something to declare it, we know to know the value, like it should be X or Y. So X or Z. So what is four state simulation helps detect the design error. So we will know with the help of this first example that it is Z, that there is short circuit, a connection is not proper, and if there is X, we will know that there is some multiple driving things are happening. So conflicts, floating connections, and missing resets, we will know all the things with the help of our two more states which has added X or Z. So we are using 4-state data types. So what are data types in Verilog? Yeah. Now the main concept is what are the data types. So there are two types of data types. There are net data types and variable data types. So as you know, in our hardware, we will store something as a memory because something should be stored now. So this storing type of thing, we will use this with our variable data types like register, memory, and everything, like our sequential circuits and our connections. For example, this block is connected to this block, so we are not storing here anything, we are just driving here, we are just driving some values, like here is 0, here will be 0, here is 1, here will be 1. So this type of connections, we will use our wire. Is the data type, you can say it is a net type of data type. So nets are like, it is driving kind of thing. So represent physical connections. This is a connection physically with the two modules, and you know the difference now, net and variable data types. So we will go further. Now first is our net data types. So connections of wires are net data types. Nets are used to connect hardware elements. As I said earlier, two blocks are connected, or two flops are connected, or two combination circuits are connected. We use net data type, and they don't hold a value. As you can see, if this is a block, here it will store value 1. Now here value 1 is reaching, so it is a wire data type, a physical wire. So wire don't care about what is 1 or 0, it will just transfer this 1 to here, and what is the value now, next value, like 0 will be there, then it will type 0. So it will store inside this memory, you can say, for now, but it doesn't care about storing the data. So wire will not store the data. So this is an example, we are using wire data type, and I will tell you this earlier, that assign statement, that left hand side should be always wire, because assign is used for driving the element. So A and B and Y are wire. So what is happening here is, like, there is an AND gate, and here is our wire, A, B and Y. So this is a combinational circuit. So as you know, combinational circuit doesn't have to store anything, so it is continuously processing the data, and here is processing our AND logic. So this is also wire, this is also wire, this is also wire. So this thing will process, so this will not store. So therefore we are using here wire data type, and wire is a physical wire, and it has a 4-state 0, 1, XZ. So this is our net type of data. So there are different type of net type of data type. So wire I have explained already. Try. So try state can be a Z, multiple drivers. Let's say this is our A, B, and here are our A, B, and Y. This type of thing you can have with our try, WAN, war, try 0, try 1, supply 0, supply 1 are different thing. This is used in switch level modeling, and supply 0 is like ground, and supply 1 is like VDD on your MOSFET. So this is power and ground nets, and constant 0 and 1 means if you are using any switch level modeling, it can be used as plus 5 volt or something, but let's say for now 0 and 1. Try 0 and try 1 try state, we mostly don't use this type of data type. For our verification engineer, design engineer use these things. I have given one example for that. So for example, if you are using wire W and you are driving, as I said earlier, assign we will use with wire or net type or data type. So W is like 1 and W is 0, so it will be conflict that it will give us X, and we don't want X, we want some value. So we use wire OR. So this 1 or 0, it will give ORing of this 0 and 1, and ORing of this is 1. So this is like that. And similar wire AND is like, it will give ending value. So if wire AND was used here, the value will be 0. So these are some data types and its uses. So next is our variable type data type. So variable will store the data. So rich, see, now this is our triggering statement, always at the rate procedure block, always is our procedure block, at assign was our continuous block, continuous assignment block, we say that. and at every passage of clock, means it is a flop, like this kind of thing. And every passage of clock, a equal to b, and this is a non-blocking assignment. I have already made the video for blocking and non-blocking, so this is non-blocking, and a will get the value of b. So this is the some process is going on here, that a will get a value of b at every passage of clock. So every passage of clock means like there is some storing element here. So in reality there will be like one flop which is a, and one flop which is b, and a will have some value, and this will give it to b, for example 1 1. So this will be storing 1 and b will also storing 1, and after sometimes if a equal to b, then a will give this value to b, then again a will give the value this b. So it is not driving, it is storing at every passage of clock. So what is happening here, see, this is a clock and this is every passage of clock. So this time period for t, it is storing this one for this time period of t, is storing this one for a time period of t. So for storing this one, this a needs some memory, and this memory is our range variable. So range will give some memory for temporarily storing this one, and a will give this to our b. So therefore we need range, and similar to our net data, we also have some data types for our variable data types. Storage I have already told, stores a 1-bit value. We can use as a vector or array. It will come next after this day 1 video. So after that there is integer. So integer is 32-bit variable. You can directly use integer and a, and you can store a 32-bit of value. It is also a posted data type, so it will store like if you are saying 0x 011 or x. So this type of number also you can store in our Verilog. Real is our real number, like it is our 0.0. It is a default value of real, and you can store a floating numbers in like that. Time is our storing a time variable. We will see this $time after some time, and this time is called system task, and I will explain this afterwards. So this time will store the time value, like for example 1 nanosecond, so it will store 1 nanosecond or something, and real time will store a real value like 1.1 nanosecond. So this 0.1 nanosecond will only store in real time. Now most important thing is reg has a storing element. So where is this? I will change the color. Okay, one sec. Okay, so I will explain you here. So wire is driving thing, and for default value, this wire, we don't know what is inside it. Its default value is z. Sorry, its default value is z. So wire we don't know anything. So its default value is z, because it is like open circuit at the start of simulation, because we haven't connected until our simulation started any block. So it will have default value as a z. And reg, we don't know what is stored inside our a or b here, so it has default value of x. So storing type of data type has mostly x as a, if it is a posted data type, it will have x as a default value. If it is real, it will be having 0.0. If it is $time, it will be having 0 nanosecond, something like this. If nanosecond is your by default time setting, like it can be picosecond or femtosecond or anything, but let's say 0 or any unit. And real will be have 0.0 as I told earlier. Okay, fine. So and rest of the net type data type will be having z. So remember, this is important. Now we are using this example of reg and var together, because we are using reg and var both at the same time. So region a and b will store the value. So it is our you can say a flop. So you can say a or b, and it will store the data and assign a or b. So a or b will store the data, and it will be assigned, a connection will be there, and here we are doing ending of our thing, and this will give us our y. So this is first of all, this is test bench, and test bench doesn't have any port. So I will explain this as like, this is our AND gate, and outside that there is our is bench TB, and this TB is connected like this. So A and B and Y. So we will give some values with the help TB. As you can see, initial begin, we have given some value as A equal to 1, B equal to 0. So for storing this A equal to 1 and 0, we are using A or B as a range as 1 1. So we will store 1 and 1 or 0 value, and it will go there. And Y is used as var because we are just watching this value, Y value. We are just watching the what is the value. But earlier, as you said, as you have seen my first example, AND gate. Yes, here AND gate. So this is a module. So here A and B are our wire, and Y is our range. Why? Because we are just giving the value A and B, we are not storing the A and B value, but we will see what is inside our Y. So you can see in your calculator, we will give some inputs. It will not store the inputs, but we will see the what is the value of output for next summation or next multiplication. So thank you. This is for today's video, and we will next meet at day 2 of Verilog course. So comment me if you want another topic.
Please, Lord, give me a sign, a sign.